So our first question was 8B. So we were talking about a roulette wheel. We want the probability it falls into a red or a green. Alright, so if you're looking for your OR, that's probability of red plus the probability of green minus the probability of both red and green. The probability of being red, all the odd numbers are red. How many odd numbers are there? I think there are 18, aren't there?
There's 18.
Out of the 38 total, plus green is the 0 and the 0, 0, so that's 2 out of 18. Minus, are there any slots that are both red and green? No. So these are mutually exclusive. You could have used the mutually exclusive formula, but if you didn't catch that, you realize right here they can't overlap, so that's just minus a 0. Oops, that's supposed to be out 38, not 18. So you get 20 out of 38, which is 0.5263. Alright. Let's look at number 10. Alright, we asked about C and G. Are there any others that you want me to work out on this problem? Okay. So on C, we are looking for the probability that they weigh between 3,000 and 3,999 grams and post-term. If you have this original data in the table, you don't really have to look at a formula. You can use it from a formula, but that's more work than you have to do. Can you look at the table and tell me how many people meet both of these requirements? Yeah, you go to the 3,000 to 3,999 and post-term, and when those meet, it's 160,354. Does everybody see that? If there is not a condition, if it's not a conditional probability, it is out of everybody, so our grand total. So you divide those and you get 0.0406. Part D is the OR. So when you do an OR, it's the probability of the first, so weighing between 3,000 and 3,999, out of our total, plus the second, so the probability of being post-term, out of our total. But what's wrong if I just add those? Yeah, we double counted those people that meet both requirements, which was what we just calculated up here. So it's probability of the first plus the probability of the second minus the part you double counted, the probability of both. Does everybody understand where I got that? If I need to put my table up here and show you where any of these numbers are coming from, just let me know. On G, I want to know if post-term and weighing 3,000 to 3,999 grams are independent. Okay, so there are different ways to decide this. If they're independent, that means knowing one thing happened does not change the probability that the other one happened. Okay, so that means the probability of weighing 3,000 to 3,999 would have to be the same as that probability given that we already knew it was post-term. So if they're independent, the conditional probability is the same as the regular. Now on part B, you found this probability to be 0.6576. On F, you found this probability to be 0.7125. Are those the same? No. So that means they are not independent. And there are other ways to figure this out. If you're looking at your formula sheet, we have on the back of the first page the multiplication rule for independent events. So the probability of both things happening has to be the same as just multiplying their individual probabilities. So that means if you multiplied your answer from part A and part B, it would have to equal our answer in part C if they were independent. So if you check that, again, it doesn't work. So there are a couple different ways you can check that independence. Seeing if the multiplication rule works, or checking if the regular probability is the same as the conditional probability. Alright, questions there?
Could you do it the opposite way, like probability post-term equals?
I just picked this one because we had already calculated the probability at 3,000 given post-term, but you could have flipped those and that would have also worked. Other questions there? So problem 11. Make sure if you miss any of these that you are correcting them as we go through. It says, according to a survey, 18% of Americans trust organized religion. So part A, what is the probability that a random American would trust the organized religion? 0.18. Okay, part B, then what would be the probability that they do not? The complement. You just do 1 minus. Okay, part C. Would it be unusual for 3 random Americans to all trust? Okay, if it's 3 random Americans, are those independent? Yes. So if you're looking at your formula sheet, the probability that the first one trusts, and the second one trusts, and the third one trusts, it tells you if they're independent, all you have to do is multiply those. It's the multiplication rule for independent events. So the probability of somebody trusting is 0.18, so you can either write that out 3 times or just do to the third power. And we get 0.005832. What is unusual?
Less than 5%.
Less than 5%. So this is 0.5%, so this is unusual. Okay, if I ask you if something is unusual, tell me more than yes or no. Make sure you're writing down your probability. Okay, you have to have something to justify your answer. Alright, D, what would be the probability that at least one does not? So we could calculate, the first one doesn't and the second 2 do, or the first and third do and the second one doesn't, or the third one doesn't and the first 2 do, or the first 2 don't and the third one does. This is going to take a while, isn't it? What's the easier way? At least one not trusting, isn't that just the complement of everybody trusting? So we just found the probability that they all trust, so we just have to do 1 minus that. And we get 0.994168. Yes?
But when we did, write it all out, why didn't that work?
It should, but you have to, it's not just one person that doesn't trust. So you have to do the 3 situations where one person doesn't, and then you have to do when 2 people don't, and then when 3 people don't, and add all those together. Other questions on that one? Yes?
What if it was at least 2 don't trust?
So at least 2, that means 2 or more. So you could calculate the probability that 2 don't. so you'd have to do every combination, you know, the first and second don't, the first and third don't, the second and third don't. You would also have to find the probability that none of them do, and then add those together.
So why do we just take 1 minus? I just don't know why we did that.
It was faster. When we were saying, okay, so we just found the probability that they all trust. And then I asked you to find the probability that at least one doesn't. Are these opposites of each other? If I took the whole class, would everybody fit in one of these two groups? Yes. Could anybody be in both groups? No. So if your groups are complements, that together they make up the whole thing, then the faster way is just to do the whole minus the probability you already know.
Why wouldn't the opposite be none trust?
Because it could be, then where would you put the group where one person does and two people don't?
So even though the at least one could be 1, 2, or 3,
Mhm.
there's only 2 options, so we can do the complement.
Yes.
Okay.
If I said like one person trusts and 3 people trust, are those complements? No, because that doesn't take into consideration everybody. If they're truly complements, it has to be like a line I can draw and everybody fits in one of those two groups. Okay. Problem 12. Because of a packaging error, a case of 12 cans of pasta sauce contain 5 traditional and 7 meat, all without labels. 3 cans are randomly selected. What's the probability that all 3 are traditional? So, traditional and traditional and traditional. And means multiply. What's the probability that the first can is traditional? Then the next case, if I've already taken 1 can out and it was traditional, how many traditionals are left?
4.
Okay, I have 2 cans of traditional sitting over here. How many are left?
3.
Okay, and if you multiply those, you get 0.0455. B, the probability that exactly 2 are traditional. So we have traditional and meat. That means I could take out a traditional and a traditional, and then my third one could be a meat. Or I could take out a traditional, a meat, and then a traditional. Or I could take out a meat, a traditional, and a traditional. Is that every situation where I have only 2 that are traditional? Yes. So then if I calculate this, probability of traditional, the next one being traditional, and the last one being meat. Or means add. The first one being traditional, the second one being meat, and the last one being traditional. Or, so plus, the first one being meat, the next one being traditional, and the last one being traditional. Alright, so then if you calculate that, you get 0.3182. Why is this not binomial? It said binomial is a fixed number of outcomes, or a fixed number of trials, which we're taking 3 cans, so it's a fixed number. There have to be 2 options, so traditional or not traditional. Why is this not binomial though? What's the other condition for it to be binomial? They have to be independent. These are not, because once I take out a can, doesn't that change the probability for the next one? Yes, so that's why we can't just use the binomial table.
Why is, like, oh my gosh, but like, why in some of like the sections is it 7/10 and the other 2 is 4/10?
Okay, so basically all of these, your denominators, the first one is 12 because there are 12 total cans. After you take out that first one, the next time there are only 11 cans in the case. After you've taken out 2, then there are only 10 cans in the case. The numerator comes from the type of sauce. So we have 5 traditional and 7 meat. So if I were taking out a meat, that means there are 7 of those. If I were taking out a traditional, there are 5. If I've already taken out one traditional, there are 4 left, so the next traditional would be 4 out of 10.
So if it said with replacement and then it came back, it would be.
Yes.
Is this the one where you told us that they're each like individual but equal the same, so we can do more 7 or 3?
Yes. Any other questions, sir? Alright. We didn't do problem 13, so nobody asked about 14. 15. Okay. So part A, we want the probability model. And I said to include the xp of x and the x squared p of x columns. Okay, so my x's, we have 4, 5, 6, and 7. To get the probability, you have to look at your table. So for the 4, x is the number of games played in the Stanley Cup. So playing 4 games happened 20 times. Out of how many total situations do we have here? 76 if you add them up. So 20 divided by 76 is about 0.2632. Okay, the next was 18 out of 76. 22 out of 76. And 16 out of 76. Do you guys know where I got all of those numbers? So you'll probably have to do that on your test. It's not hard to find those probabilities, but you have to remember, you need to add up all your frequencies and divide. It's just like saying on my test, I had this many A's, this many B's, this many C's, this many D's. So you're finding out the probability of each score. Okay, xp of x, you're just multiplying. So 4 times the 0.2632, 5 times 0.2368, 6 times 0.2895, and 7 times 0.2105. I know I'm not really showing you a lot of work here. If you are lost, speak up. Okay, these tables, this will be a lot of points, not because it's hard, but because you're calculating a lot of values and we'll have to use it to find some things in a minute.
On the test, will the question be worded like this one where like x times p of x is in the problem?
Yeah, I'll probably say to include that in your table. Okay, last column, x squared p of x. So 4 squared is 16 times 0.2632. 5 squared is 25 times 0.2368. 6 squared is 36 times 0.2895. 7 squared is 49 times 0.2105.
So if it did not ask for the xp of x or the x squared p of x, we just do a basic one? Just
your probability distribution, yeah. So technically the probability distribution is just the x and the p of x columns. But because I'm going to have you calculating the mean and standard deviation in a minute, that's why I had you go ahead and do both of them.
Okay.
Alright, on part B you didn't ask about it, but when you draw the graph you are just doing the probabilities. So we're pretty good with that. You just go mark your x's and draw it up to the probability. You didn't ask about C, but I'm going to go ahead and do it. So look at your formula sheet. Did I say anywhere that this was binomial? No. And in fact, if I had you calculating your xp of x and x squared p of x, it's not binomial. We're doing the other one on here. So just for the mean of your random variable, it says on here what does this funny looking E mean? The sum of the x times p of x. So you're just adding up everything in that column. And we get 5.446. D, our standard deviation, if you're looking at your formula sheet, there are two options. We always did the second one, because if you look at it, it's got that sum again, but it's the x squared p of x, and we already have the x squared p of x in our formula, or in our table, minus the mean squared. So the sum of the x squared p of x, you add up your final column, and that turned out to be 30.8677, minus the mean, which we found on part C, squared, and we get 1.093. Alright, so if you've made that table, you've already done all the hard work. Then it's just a matter of adding some things up and plugging in your formula. Are we okay with that?
Okay, so you only use the binomial mean standard deviation when it says binomial?
Yes, but it has to be binomial. So I either have to tell you it is binomial, or I have to give you the information to confirm that it's binomial, which is a fixed number of trials, only two possible outcomes, and everything independent. I didn't give you anything along those lines here, so we can't assume it's binomial.
So then we just use the other two?
Yep.
If it was binomial and we still did this,
It would work. So like problem,
On,
like,
maybe it was like 20 or something.
yeah, 18, 19. On neither one of those did I say it was binomial, but we can think about it. Like on 18, we're talking about the probability that they die within a year. So is that a yes or no type thing? Yes. Okay. Are they going to be independent? If I just take two random people in the U.S., yes, those are independent. If you look at part A, I want exactly 1 out of 10 visitors, so I have a fixed number of trials, so that's binomial. So I didn't specifically say this is binomial, but I kind of led you along those lines. I didn't give you a table of probabilities or frequencies, and I told you how many trials we are going to have. I told you your probability. All right, problem 16. All right, we've had this on a homework, we've had it on a review, we did like 2 examples in class on it. It's on your study guide. I bet you're going to see it again tomorrow, okay?
Yeah.
So, if I ask you for expected value, what am I asking you for?
How much money they're gonna make?
Yeah, that's just the mean. If you don't remember, it's on your formula sheet. It says mean and then in parentheses expected value. And it tells you it's the sum of x p of x. So we need our x and our p of x. So there's 2 options here. Either the person lives or they don't. Those are my only 2 options. So the probability of the person living is 0.999544. Okay, if they live, then what happens with the money they paid for their policy?
They lose it.
They lose it. The company gets to keep it. We're finding the expected value for the company. So if this person lives, the company makes money off of them, right? And how much money did they make?
$300.
Alright. Now, how would I find the probability that the person does not live?
Take the column.
1 minus that. Oops. So you get 0.000456. Now, if that person dies, then the company has to pay $250,000. So they're losing money. They don't lose all $250,000 though, right? Because the person did purchase that policy at the beginning of the year. So the person has paid them $300. So the amount they lose is $250,000 minus that. So they lose $249,700 if that person dies. Does everybody understand where I got these numbers? So, mean is just the sum of x p of x. So you multiply those things together. I didn't break it up on mine. probably turn out to be a positive number, right? If it's turning out to be negative, then the company isn't charging enough for their policies. They don't want to lose money when this is all said and done.
Okay, so I like rounded my P of X's.
Don't do that.
See how many.
Yeah, cause that gave me the really long numbers.
Uh-huh.
I got
Especially
175.
when I give you the whole probability as a decimal to begin with, use the number I gave you.
Okay, because I was like, I think I did it right, but I got 175.
Yeah, in this scenario, especially where this number is so small to begin with, a little bit of rounding makes a huge difference on your final answer.
Okay.
Alright. Number 18. So, problem 17, we started talking about the binomials. 18 and 19, I've already kind of mentioned. These are binomials, so some good things to think about when trying to decide if it's a binomial, like I said. I have to give you the probability of success, and it has to be the same every time. So that wasn't the case for my pasta sauce because the probability of getting a meat sauce changed as you took more cans out. But here, the probability every time is 0.05. So I gave you the probability of success. So on part A, we want the probability that exactly 1 of 10 visitors. So the P, probability of success, will be 0.05 because we're finding the probability that they survive. We're finding the probability that they die, which is the 0.05. Q is 1 minus that. So on part A, my N is 10. What is my X? 1. So that's like saying 10 choose 1, 0.05 to the X, 1 minus P, so 0.95 to the N minus X, 10 minus 1 is 9. Or is this one where we can use our table?
Yes.
Yes. So in general, if the probability is on your table, use your table. There are a couple on here where I said to calculate, like on problem 21. If I say to calculate, I want you to write this little piece out from your formula and put it in your calculator. So you need to know how to do both things. So N equals 10 is the back of the second page. Our P is 0.05. You're going to X equals 1, and you get 0.3151, which is the exact same thing you would get if you put this in your calculator. So you can use either option. Table is going to be faster, but both of them work. Does everybody know where to get this on your table? Back of the first page, we are on table 3, just our regular binomial. N equals 10, X is 1, P is 0.05. Remember in that packet, the first 2 pages are your regular, second 2 pages is cumulative, so they've added everything less than that. Okay, so B, the probability that fewer than 2. So if it's fewer than 2, then X could be what? 0 or 1. And N, how many people do we have this time? 25. Does my table go up to 25? No, I did this intentionally, so you had to do it by hand. So we have 25, choose 0. My 0.05 to the X power, X is 0. My 1 minus P, so 0.95 to the N minus X, 25 minus 0 is 25. We also need to find the probability of 1. So 25 choose 1, 0.05 to the first, 0.95 to the 25 minus 1 is 24. It's like saying 1 person dies and 24 survive. Or nobody dies and all 25 survive. Then you just put those in your calculator. And your total answer is 0.6424. I just plugged it all in at once. You can do them individually. Does everybody know how to get like the 25 choose 0 part? You put it in parentheses. So you do parentheses 25, hit your map over to probability, and it's the third one, NCR. And then you put your 0 and close that parenthesis.
Do we gotta show that work tomorrow?
No, but if you got the wrong answer and I didn't have anything to know what you were trying to do, then you would lose all the points. So a problem like this would probably be worth 2 or 3 points. If you get the right answer without showing me any work, great. If you showed this line and just had the wrong decimal, you would only miss 1. Alright, on part C. We want the probability that at least 8 of 10 will not die. Okay.
That's D.
Oh, sorry. C, the probability that at least 2 of 25 will die. So we just found the probability that less than 2 die. Now I want at least 2. So that means X could be 2 or 3 or 4, all the way up to 25. Do you want to calculate all of those? No. What's the faster way? Part B is just the complement of this. So we get 0.3576. So I'm probably going to do something like that somewhere in your test, just checking if you're paying attention to your complements. It saves you a lot of time, so you don't have to recalculate everything. Alright, is everybody with me on that one? Know where I got those numbers. Alright, part D, the probability that at least 8 of 10. So this one though says will not die. We have to be very careful. P is the probability that somebody dies. So my X needs to be the number of people that die. So if at least 8 of 10 do not die, then how many can?
0, 1, 2.
Alright, so everybody agree with that? So if at least 8 people survive, sorry, did I say that right? At least 8 of 10 will not die. That means only 0, 1, or 2 could die. So everybody with me there?
So I didn't do it like that. That's so it's the same as.
Did you change your P to 0.95?
Yeah.
Yep, that works too. So then I went back to when my N is 10, so could we just add this up on our table?
Yep.
Yes. So you could use the same one we were just looking at and just add up your numbers for 0, 1, and 2. This would be a scenario where you could use the cumulative table. If you get confused on when to use the cumulative table, then my advice is just never use it. Because there is no reason that you would have to. You could always get it from the other one.
Could you, after you're done with this one, could you do it off of the cumulative table?
So we get 0.9884. If you did the cumulative table, so everybody flip, cumulative table is your table 4. We want N to be 10, so we're back the second page there. Our P is 0.05, and we wanted less than or equal to 2. So if you go to your 2, you get 0.9885. So just slightly different due to rounding. Yes, ma'am?
So on this one, I did the 8, 9, 10, which I know now why I did it, but if you use your table, it was 0, 0, 0. So in like that case, what would you do? You just have to like actually work them out?
We just did.
Yeah, so basically what it's saying is your first 4 decimals are all 0, so you have to work it out.
Okay.
If you were using the 8, 9, or 10, those were the people living, so your P would have to be the probability that they live, which is 0.95, and that would be another way to do it.
So I did 8, 9, 10 too, but I'm confused with the way that you're doing it because like why are you using 0, 1, 2?
Because it's the P, the 0.05 is how many people died. So if 10 people lived, nobody died, so that's 0. If 9 people lived, then 1 person died, so that's 1. If 8 people lived, 2 people died, so that's 2.
Yeah,
Okay.
so that's what we used to do. Right, and was 10
So,
if you get
I
enough
got that
problems.
answer here, but if I did it like
Yeah, but
went to this probability and then to 8, it's not the same.
Because this would want to add up 8 and 10. And when you look at 8, that's adding up to 0 to 8.
Like that one, we could just.
So you would need to do the other table.
From the other table, you got
Lots of good questions, guys. Part E. In a random sample of 1,000 ER visitors, how many are expected to die within the next year? Expected value. When I say expected value, what am I talking about? The mean. Okay, this is binomial. So if you look at your formula sheet, in a binomial distribution, mean is just n times p. So we are talking about 1,000 visitors, so my n is 1,000. We want the probability that they die, which was 0.05, and we get 50. Standard deviation from your formula sheet is square root of n times p times 1 minus p, or q. So that'd be the square root of 1,000 times 0.05 times 0.95, and get 6.8920. All right.
Wait, where did you get standard deviation?
I like the formula.
Yeah.
The right under top of the second column on chapter 6, the mean and standard deviation of a binomial random variable.
Is it the first one?
The mu is n times p. That's your.
Oh.
Yeah,
never
we're doing
mind.
binomial,
I'm
not
looking
just
at the wrong
regular.
thing.
Okay. I don't think we're gonna get through the rest of these. Let's try. So 19, it is again binomial. 60% would be our p. We have a random sample of 15 people, so our n is 15. So part C is at least 5. So that means x could be 5, 6, 7, all the way up to 15. So we could just add all this. Oh, I skipped B, didn't I? All right, let's do B first. All right, so fewer than 5. So that means x could be 0, 1, 2, 3, or 4, right? Is 0.6 on your table? Yes. Since we're adding all these up, that would be an excellent time to go to your cumulative table. That's table 4. Our n is 15, which is the very back of your packet. P is 0.6. And we are adding up everything to 4, so you go to 4, and it gives you 0.0093. Part C wants at least 5. So that means 5, 6, 7, all the way up to 15. What do you notice about these things? They're complements. So you can just do 1 minus the probability you just found, and you get 0.9907. Yes?
There was one on the homework, I remember I asked you about that, we had to like add 3 and 4 together and then do that. So on this one, I added the 4 for some reason into the 5. Like when would we add?
If you hadn't just found the complement, like on part B, if I'd said fewer than 4, and so we hadn't actually done this one, and then part C, I wanted more than 5, so we had to calculate some more.
How do you know when to use table 3?
Table, you can always use table 3. I use table 4 when I'm adding up things. So since I started at 0 and went all the way to 4, that's a good time to use table 4. If you're not sure, always use table 3 and just add up everything.
And when it's a table, the number you go to is like all the previous numbers of